Welcome back, everyone. In today's video, we're going to be talking about p-values. So to begin with, what is a p-value? A p-value is the probability of obtaining the data that we got if the null hypothesis is in fact true. P-values are not the probability of a null hypothesis being true. Hypotheses are not random trials, so they don't have a probability associated with them. The null hypothesis is either true or not true, and we'll never know. Our samples, on the other hand, are random trials. They're random subsets of the population, and as a result, they have a probability associated with them. When the null hypothesis is true, there's a certain probability of getting different outcomes that's due to our sampling error. So there are probabilities associated with samples, even though there aren't probabilities associated with hypotheses. A p-value is a probability, and as a result, it ranges between 0 and 1. When p-values are small, then the null hypothesis is inconsistent with the data. It's unlikely that we would get data like we got if the null hypothesis is true. And as a result, when our p-value is small, we have some evidence against the null hypothesis. And if that evidence is strong enough, that is, if the p-value is small enough, then we reject the null hypothesis and instead accept the alternate. So the smaller the p-value, the more evidence we have against the null hypothesis. So how small does p need to be before we reject the null? Well, typically in biology, we reject the null hypothesis when the p-value falls below 0.05. And this value of 0.05 that acts as a threshold for rejecting the null hypothesis is what's called the significance level. We determine this threshold ahead of time, and as I mentioned, it's usually 0.05, although not always. And if our p-value falls below our significance level, or alpha, we reject the null hypothesis. And if our p-value is greater than alpha, then we do not reject the null hypothesis. The convention in biology is to use an alpha of 0.05, but there are other values that are sometimes used. But these need to be predetermined before you analyze your data. It's not okay to simply adjust your alpha to make sure that your p-value falls below it. So what does alpha represent? Alpha, or our significance level, represents the probability of making a mistake and rejecting the null hypothesis when it is actually true. So when we set our alpha before our analysis, then what we're doing is stating that we're comfortable with a certain probability of making this type of error. We're okay with 5% of the time making the mistake and saying that there is in fact an effect when there actually isn't. There are actually two ways in which we might make a mistake in our hypothesis testing. The first one we've already talked about is referred to as a type 1 statistical error. And that's a situation where we reject the null hypothesis when it is in fact actually true. And we're going to make this mistake in statistics with some frequency alpha, that is our significance level that we set typically at 0.05. So we're comfortable then saying that 5% of the time, we're going to make one of these type 1 errors where we reject the null hypothesis when it is in fact true. But there's another type of error that we can make in our hypothesis testing, and that's what's referred to as a type 2 statistical error. A type 2 statistical error is when we fail to reject the null hypothesis when it's in fact wrong. So the null hypothesis is incorrect, but we don't have a sample that has sufficient power to be able to discriminate that effect. And that's what's referred to as a type 2 statistical error. So in two scenarios, we can be correct. We can correctly retain the null hypothesis when it's in fact true, We can correctly reject the null hypothesis when it's actually wrong, but there's two ways in which we can make statistical errors, type 1 and type 2 statistical errors. You can think of a type 1 statistical error as being like a false positive, claiming an effect that is in fact not true, whereas a type 2 error is like a false negative. There is in fact something going on, but you failed to detect it. Now, I mentioned that in addition to the two ways in which we might make a mistake in our hypothesis testing, there are also two ways in which we might be correct. And since probabilities must always sum to 1, then if our null hypothesis is correct, we can either reject the null with probability alpha or fail to reject the null with probability 1 minus alpha, because these two probabilities need to sum to 1. And we can refer to these two scenarios where we might be correct as referring to statistical power, or the probability of detecting a true difference, and statistical confidence, the probability of correctly retaining the null hypothesis. Now, these are the two types of statistical errors that are most frequently discussed, but there is a third type of error that is rarely discussed in statistics, and that's sometimes called a type 3 statistical error. A type 3 statistical error occurs when the researcher correctly rejects the null hypothesis, but misattributes the cause. This can arise from having an improper experimental design or having some other confounding factor that hasn't been controlled for. So what value should we be using for our alpha or our confidence level? Well, the field of biology has generally settled on an alpha of 0.05, where we are comfortable with a 5% chance of falsely claiming an effect and rejecting the null hypothesis when there in fact is not an effect. But it's important to recognize that this threshold of 0.05 is completely arbitrary. We really need to give some thought to whether or not we think that 0.06 is really all that different from 0.05 or 0.04. And if we get a p-value in this marginal range that are falling in the category of 0.05 to 0.1, where we have some evidence against the null, but not substantial evidence against the null, then we need to give some thought to what are reasonable claims in this scenario. It's not true that biology follows these sorts of thresholds where effects are true or not true depending on which side of the threshold they fall on. And yet we use this strict threshold quite religiously within the field of biology. And I'd say we really ought to give that much more careful consideration. One situation where we would need to use an alpha that was different than 0.05 is when we perform multiple statistical tests of the same biological hypothesis. So let's say we were interested in testing the biological hypothesis that flower size differs between two populations. We go out and we measure 50 flowers in each of those populations. But when we measure the flowers, for each flower, we collect 20 different measurements of size. So instead of having a single size measurement for each flower, we've now got 20 different measurements, like petal length, stem height, distance between the leaf nodes, those sorts of things. And the problem arises is that if we were to perform 20 different statistical tests, one for each of those flower measurements, to test the same biological hypothesis that size differs, then we would expect that 1 out of every 20 statistical tests would falsely reject the null hypothesis at an alpha of 0.05, because that's what 0.05 means. 5% of the time, or 1 out of every 20 statistical tests, will falsely reject the null hypothesis. So instead, when we are using multiple statistical tests to address the same biological hypothesis, we need to correct our alpha level. One of the approaches that's used to do this is referred to as a Bonferroni correction. In a Bonferroni correction, instead of testing at an alpha of 0.05, we take that alpha and divide it by the number of statistical tests that we're performing to come up with an adjusted alpha level that we use for testing our significance. Now, this Bonferroni correction is known to be a little bit too conservative, which means that it penalizes or reduces that alpha too much, more than it should. And so there is a second approach that's been proposed called the sequential Bonferroni correction. Okay? And in this sequential Bonferroni correction, we test our largest effect, or let's say our size measurement with the biggest difference between those two populations, and we test that at our typical Bonferroni level of alpha divided by k, which is the number of statistical tests that we're going to perform. But then after we've tested this largest effect and move on to the next largest effect, we test that at a slightly different alpha that's a little bit bigger, because instead of dividing by k, now we're dividing by k minus 1. When we go to the third largest effect, then we divide alpha by k minus 2, and so on. And what we're doing is that for each of these sequential tests, our rejection criterion, our alpha, is less stringent because now there are fewer comparisons to be made. So let's say we had 20 statistical tests. For our biggest effect, we would divide alpha by 20 and test at that level. But then after we've already done that, we only have 19 remaining tests, so we divide alpha by 19. Now, it's not always so clear-cut to know when you need to correct your alpha for multiple tests and when not. Sometimes it's not so clear what represents the same biological hypothesis and what are statistical tests of unique biological hypotheses. Are all of the analyses within a single manuscript the tests of a single hypothesis, or are there multiple hypotheses within that manuscript? Sometimes when we're reporting results, we tend to put the multiple tests of a single biological hypothesis within a single table in the paper. And so we might think of this rule of thumb then of trying to maintain a table-wide error rate of 0.05 by dividing that 0.05 by the number of tests within that table. At the end of the day, it's often a good idea to present your results both with and without a correction for multiple tests so that the reader can draw their own conclusions. There are other situations in which we should give some thought to what an appropriate alpha level is, even when we don't have repeated statistical tests of the same biological hypothesis. Remember that our alpha level represents our probability of falsely rejecting the null hypothesis. And we typically set that alpha level at a very low level because we're very reluctant to claim an effect when in fact there isn't one. So the weight of evidence then is strongly stacked in favor of the null hypothesis. And that's okay when, for example, our null hypothesis might be no benefit of a vaccine, and we want to be sure that there is in fact a benefit before we actually claim one. But what happens when the null hypothesis is that there's no effect of a particular habitat on the abundance of an endangered species? And if we err on the side of showing no effect, then maybe a developer comes in and builds their subdivision in that habitat and the endangered species is lost. Maybe in these sorts of situations, we might be better off with a statistical test that uses a higher level of alpha and puts less weight of evidence on the null hypothesis and allows us to more easily reject that null hypothesis. So we need to think carefully about what the costs of a type 1 or a type 2 error are. And there are potentially big differences between a null hypothesis that's about no benefit of a particular action versus a null hypothesis that's about no harm. If we're erring on the side of caution and stacking the deck in favor of failing to reject the null hypothesis by setting a very low alpha level, then we might in fact be stacking the deck in favor of concluding that there is no harm to a particular land use or the particular chemical flowing down into a stream. And in these situations where a null hypothesis is about no harm, perhaps we ought to use an alpha level with a higher value that allows us to more easily reject that null hypothesis and be less afraid of making a mistake of claiming an effect of harm in this case, as opposed to reverting to the null hypothesis of no harm. In the examples that we've talked about so far, we've always been referring to what are called two-tailed or two-sided probabilities. If you recall from our example of the sample of right-handed toads, where 14 out of the 18 toads were right-handed, and we wanted to calculate the probability of getting a sample as extreme or more extreme than that if the null hypothesis were true, we needed to add up the probability of getting 14 right-handed toads, 15, 16, 17, and 18 right-handed toads, as well as the complement where the sample was skewed towards left-handed toads. That is, we needed to consider probabilities at both ends of this sampling distribution. And this is what's referred to as a two-tailed statistical test. But we might also have a situation where we have an alternate hypothesis that doesn't simply claim that there is a difference, that right-handed and left-handed toads differ in frequency from 50-50, but we might have an alternate hypothesis that is in fact directional, that states a clear direction. That is, that right-handed toads are more common than left-handed toads, or that mean body temperature is greater than 98.6 degrees Fahrenheit. Not just different from 98.6, but actually greater. In these situations where we have a clearly directional alternate hypothesis, we only reject the null when the data depart from the null in the direction predicted by the alternate hypothesis. And we then calculate our probability using only half of the distribution, or the end of the distribution corresponding to that direction. So if our alternate hypothesis was that right-handed toads were more common than left-handed toads, then we would calculate our p-value by simply adding up these probabilities, and we wouldn't add in these probabilities down here. And that would be referred to as a one-tailed statistical test that we use when we have directional alternate hypotheses. Now, those of you who are keen-eyed might notice that whenever we have a one-tailed statistical test, our p-value is going to be half the size that it would be if it was a two-tailed statistical test. So this means that, of course, we need to decide a priori before we collect our data, before we analyze our data, whether we're going to be using a one-tailed or a two-tailed test. We can't simply decide after the fact that we would rather have a smaller p-value, and so we're going to use a one-tailed test instead of a two-tailed test. That would be an unethical decision to make. And in fact, some fields frown upon one-tailed tests altogether, and in general only accept analyses based on two-tailed statistical tests. So what happens then when we fail to reject the null hypothesis? In these situations, although we don't have much evidence against the null hypothesis, it's not appropriate to say that we accept the null hypothesis. That's why I've been using this somewhat clunky terminology of not rejecting rather than accepting. So even when we fail to reject the null hypothesis, there's still a chance that we're wrong and that null hypothesis is actually false. And so we choose not to use the words accept the null. Instead, we use the words that we fail to reject it, or perhaps that we retain the null. And what we find is that many studies in ecology and evolution actually have not a lot of statistical power to be able to reject the null. And so in many cases, the results of the statistical tests are in fact inconclusive. And what we really need is more data to be able to have a more powerful test to be able to discriminate between a true absence of an effect versus a study that didn't have enough power to detect an actual meaningful effect. It's important to recognize that statistical and biological significance are not equivalent. Statistical power and our ability to reject the null hypothesis and find a significant effect is determined in large part by sample size. So we can create very powerful statistical tests with very large sample sizes that are able to find statistically significant patterns in the data, but that are biologically trivial. On the flip side, studies with very limited sample sizes can result in very important biological effects that are statistically indistinguishable because of the limited sample sizes. And so oftentimes we might be interested in trying to discriminate between a result that is biologically significant versus a result that is statistically significant. So it's important then to present our results documenting the magnitude of the effect and to decide ahead of time how large an effect would represent a biologically important result before we perform our statistical tests. It's possible that with a small study, we might detect a biologically important effect, even if this is not statistically significant. But it's important not to fall back on biological significance as some sort of crutch for non-statistically significant results. It's important to determine ahead of time what you would deem to be a biologically significant effect size or difference before we perform our statistics. Remember that even if we think that an effect size of 0.5 be biologically significant, this result tells us that we don't have a lot of confidence in what this value of 0.5 actually is because of the very high amount of variability around that value. We've talked a lot about p-values and their interpretation, but I want to spend a little bit of time talking about how we ought to report our statistical results. While our conclusions about our null hypothesis are based on the p-value, it's never sufficient to report the p-value alone. If we want to comprehensively report the results of a statistical test, we always need to include some measure of the value of a test statistic, a measure of the magnitude of the effect size, some indication of the sample size or degrees of freedom, along with the p-value. It's never sufficient to report just a p-value on its own. The last bit of suggestions with respect to reporting statistical results is that we generally reserve the word significant to refer to statistical results rather than using it as a synonym for importance. So here we have an example of a statement from perhaps a results section of a paper that says that soybean plants that were experimentally stressed had leaves that were significantly smaller than control plants, followed by the results of the statistical test that we used in this case. The leaves of stressed plants were on average 39.6 centimeters squared, smaller than control plants. So these two sentences in our results include some indication of the significance of the results as well as the direction. Our statistical results, including our test statistic, our degrees of freedom, and our p-value, as well as a measure of the effect size. How big was the difference in this particular case? So here we have all of the ingredients of an appropriate reporting of statistical results. Some indication of significance and direction, statistical results including test statistic, degrees of freedom, and p-value, as well as a measure of the magnitude of the effect size. So in summary then, hypothesis testing is a useful and well understood statistical framework, but we still need to think about it. We need to give some thought to what it means to have rigid thresholds for our alpha level. And is it really all that different to have a p-value slightly below or slightly above our predetermined alpha? It's also important to recognize that p-values are very helpful, but they're not everything. We also need to consider effect sizes and the magnitude of the effects that we're talking about. And especially when it comes to reporting our results, we need to remember that statistics aren't everything and that we do biology because of biology. So we should always make sure that our statistics support our biology and don't replace our biology in our science writing.